Dr. Pettit, I'm Pam Zelps, and I just want to do a brief introduction, if that's all right with you.
Okay.
First of all, I want to thank everybody for coming to the virtual appearance of Dr. Don Pettit. I would like to thank NASA for helping us put this on. In addition, I would also like to say thank you to Chip Shepard. He was very instrumental in making this happen for us. Dr. Don Pettit is the veteran of 3 space flights. He's logged over 370 hours in space, 13 hours plus in spacewalks. He's lived aboard the International Space Station 2 different times, once for 5.5 months and once for 6.5 months. Dr. Don Pettit is also an inventor. And that is one of the purposes of this phone call this morning, is because I have a team of students that is going to be working with Dr. Pettit on one of his inventions. So the way we're going to start this program is we're going to allow the 3 young men up front here, Michael Vasquez, Julian Garcia, and Kevin Edney. We're going to allow them to ask questions of Dr. Don Pettit about his invention. Once that is completed, then we will have time for students to ask questions. What we would ask from you, faculty, as well, okay? What we would ask from you is that you step up to the mic to ask the question, because we are recording this session for the online class, okay? All right, so Dr. Pettit, these are my students, the 3 that will be working on your glue, and I know they have several questions ready for you. So let's go ahead and get started.
Hi, good morning, Dr. Pettit. My name is Julian Garcia, and so our first question was, does the glue exhibit thermal expansion characteristics?
Oh, of course, everything, when heated, either expands, and there are a few things that contract, and so this is a silicate-based glassy compound. I assume you're talking about the DPG? Yes, sir. Yeah. So it was a sodium silicate, silicon oil-based compound that when heated, it decomposes basically to glass, and glasses expand and contract, and so there is thermal expansion and contraction with this.
With a follow-up question to that, what happens after it's heated or it's used? How does it come off? Does it just?
Well, you don't want it to come off. That's because the whole purpose of this glue was to glue patches on the leading edge of the wings on the space shuttle that have been damaged in orbit, and you don't want this stuff to come off. So it goes on as a goop, as just something like a putty or a spackle, and then you put it underneath a patch, and then you use a little screw to hold the patch on, and then in the process of atmospheric entry, it gets heated to about 2,000 degrees centigrade, and in the process of heating, it bonds onto the leading edge and adds an extra bonding agent in addition to the threaded fasteners.
Okay, what are the flow properties or the rheological properties of the goop? You know,
in order to put numbers on it, you need to measure it in some kind of a viscometer, usually a rotary viscometer or a cone-shaped viscometer, and I didn't do that. What I did was I started off with silicon oil that was fairly viscous. I'm trying to remember the viscosity. I think it was around 100 centistokes, if I remember right. I should have looked at my notes before I came here, and so it's fairly thick, maybe like maple syrup, and then you mix a number of other particles with it. You mix silicon carbide particles in with this, plus other powdered borate-based glasses to act as a frit. and then the whole thing, and you need to have a mixture that won't bubble and foam when it's subjected to a vacuum. That's because there are a number of these frit compounds that here on Earth they behave well, and you can put them in a kiln and you can heat them up, and they'll basically bond two pieces of glass together, but they won't work in a vacuum. They'll just bubble and foam, and so this stuff had to remain like a putty-like material, so you could spackle it on, and it would flow, but it had to be that way in the vacuum of space, and that's where the silicon oil was useful, because it has a real low vapor pressure and it will remain a nice, well-behaved liquid even in a hard vacuum. And so to directly answer your question, I didn't measure the rheological properties per se. What I did was I started off with something that I knew what the viscosity was, and then I added material to it, and it increased its viscosity to the point where it wouldn't free flow, but you could spackle it on sort of like a spackling compound that you use to plaster your walls.
Very good.
All right. Well, Dr. Pettit, my name is Michael Vasquez, and I will go ahead and go with these next questions here. Currently, you said that it's the boron or the borate glass is being used as the filler. Is there any other substances that we could use as a filler which might lead to its use in different environments?
Yeah, the borate-based glasses lower the melting point, and they also help clean the surface that they're bonding to, and it acts as a wetting agent. So silica by itself, if you were to put powdered silicon dioxide in the silicon oil, that has such a high melting point, and it doesn't tend to wet a lot of material. So if you mix borate-based glasses with it, then it will make, upon heating, it'll make a material that has a much lower melting point, and it free flows easier, and then it will lower the wetting angle so that it'll kind of creep across the surface, and that's what I wanted in terms of using this as a compound to glue the patch on. And there's one other detail that's important with this compound. If you put, and this is particularly this is optimized for repairing a carbon-carbon composite leading edge on the space shuttle for entry. If you put a patch, say you got a hole, maybe the hole is 2 inches in diameter, and you have a patch that's 6 to 8 inches in diameter, and you have a little toggle bolt, and you can stick it through the existing hole and then screw this patch down over the hole. Around the edge of the patch, because of the compound curved nature of the leading edge, there could be little gaps where the patch doesn't completely conform to the surface. And those gaps, it turns out, in atmospheric entry are really, really bad. You can get atomic oxygen streaming underneath the patch through that gap, and then it will start to erode everything, and you'll burn a hole through. And so this material, this compound, not only does it melt and form a bond glue kind of material, but it keeps the atomic oxygen from running through little cracks around the edge of the patch.
And if you don't mind, could you please describe the physical properties of the dual-purpose glue when it's not in a vacuum?
Okay, its color is kind of a dark green, and that comes from the silicon carbide particles that you put in there, and it's thick. You could take a dollop of it and put it on the table. Say if you had something about 20 millimeters in diameter, you could pile it up, and it would probably you could pile it up into a little stack, and it'd probably be 20 to 25 millimeters high. So it's not a liquid that if you put a liquid on the table, it would kind of run out into a thin pancake. This stays sort of, I guess the best analogy is the spackle compound that you use plastering walls, and the compound used with seam tape when you put drywall together. And it's a thick, pasty material that if you stir it around a little bit, it gets a little more viscous, and then you take your spackle tool and you smear it around on the wall, and then it sets up as a thin layer, and that's kind of how this stuff behaved. And you could put a coating of it on the back of the side of the patch, and then you'd stick the patch on the leading edge of the shuttle, and then you'd screw it down, and this stuff would kind of ooze out around the edge of the patch. And then you could take a spackling tool and just kind of smooth the stuff up around the edge, and then you're done for the day. You're ready to fly the space shuttle back into the atmosphere.
Okay, so could you please describe the curing process or the series of phase changes that it goes through?
So it starts off as this sort of thickish spackling compound, and as you heat it, first you put it out in the vacuum of space, and it behaves well in the vacuum of space. It doesn't foam, it doesn't bubble, which are things that you don't want it to do. And so it behaves pretty much the same in the vacuum of space as it does if it's sitting on your tabletop here on Earth. And that's by design. And then, so you've got this patch with this compound underneath the patch, and you've kind of smoothed up the edges. Then during the atmospheric heating stage, this stuff decomposes the silicone-based vehicle, the silicon-based oil that carries all the particles, basically decomposes and turns into glass, and that mixes with the borate-based frit material, which forms this low melting point glassy material that wets both the patch and the leading edge of the shuttle, and then it can kind of crawl around and make sure that it has good bonding. And then the silicon carbide just acts as a highly refractory grit compound that's inside of the glass. It builds up the matrix and makes it more resistant to being attacked by atomic oxygen. And let me also make one more point. And as you can see, this invention was highly optimized for use on the leading edge of the space shuttle to protect it for atmospheric entry when you had a hole in it. And so it will be interesting to see whether you guys could dream up other earthly uses of this stuff, and which will be interesting to see. But for this patch compound, during the high heating phase, the atmospheric drag forces are low. So you don't really need to worry about the patch falling off when it's really, really hot. Now, after you have slowed down and now you're in the atmosphere and you're actually flying like an airplane, or a glider in this case for the shuttle, that's when you have high atmospheric drag, and that's where you need to worry about the patch possibly coming off, and that's where the glue bonding comes into play with this material, so that during the high heating phase, the glue acts as a gap filler and keeps the atomic oxygen from working its way underneath the patch and burning another hole. During the atmospheric part of flight, that when it's cool, that's when it acts like a glue and helps keep the patch on from the high aerodynamic forces.
Dr. Pettit, my name is Kevin Ebney, and first I want to say just thank you for being here with us. It's a high honor to be sitting in front of you. If I could ask about, I want to go back to our very first question, and just to clarify, after the shuttle re-enters the Earth's atmosphere and lands, and it is being getting ready to go back into storage, if you will. I'm not exactly familiar with that process. What does the glue look like at that point? What does it feel like? What does it look like? So it's been superheated.
Yeah.
And then it's come all the way through to room temperature, air temperature. what is it then?
Okay, it looks kind of. Well, you imagine this glue is kind of creeping out from underneath this patch, and it kind of has a dark greenish color, and there might be a little bit of white fringe around it. And I know this just from the testing that we would do in vacuum chambers here on the ground. And you also have to remember that this is not considered a permanent thing. This is a contingency repair to get you through the atmosphere and still be in one piece. And after you land your spacecraft, that particular section of the leading edge is going to be removed and replaced with a new section. So this is a use once to get you home in one piece kind of thing. And after that, you can take this chunk of the leading edge off and put it in a display case someplace so everybody can look at it. But you're definitely not going to want to use that piece again.
Okay, I understand that. So would it return to the putty state, or because?
No. I understand your question now. Once you heat this stuff, you irreversibly decompose the silicon vehicle, and that coupled with the borate-based frit and the silicon carbide powder may basically turn it into another form of glass. And wherever it happens to be stuck to is where it's going to stay after that. So it's an irreversible bonding action. And by the way, the size of the silicon carbide powder, I believe it was around 5 micron was the diameter of the silicon carbide powder.
All right, that clears that up, and we wanted to make sure we got to that.
Because this is a use once kind of thing.
In the next few questions after this next one is going to be more into the application of potentially what it could be used for, but as a kind of a final one and just understanding the properties of the glue.
Okay.
And you may have it in front of you, but can it be unbonded? So it went through a bonding stage. Can it be unbonded with ultrasonic agitation? So that ultrasound type agitation, would that create the shear or what it takes to remove the bonding properties from it?
Probably not. If it was really bonded to a material. So remember, this is a glassy material, and it will wet things like other ceramics, and it will, think of it more like a glaze. Once you put a glaze on a pot, that glaze is there to stay. I mean, the glaze may craze, but you're not going to remove the glaze. And so think of it kind of like a glazing for ceramics, and except it's it's like a putty kind of a compound that you can smear around, and then upon heating, it turns into a glassy material that can creep across the surface, and so from that respect, it's more like a glaze, and it will stick to metal surfaces, and it will stick to other ceramic kind of surfaces, and carbon composite. In some respects, you could think of it as a ceramic, and so once it's stuck to the surface, it's there.
All right, that's great. We did want to get into some questions about specific uses, and Michael is going to ask a couple right now.
Okay, it'll be interesting to see what you guys have dreamed up for this.
All right. So because of the heat barrier-like characteristics that the borate glass does provide, and your glue does provide, for outside of the space aircraft, can this be used, for example, to coat the walls of a nuclear reactor, whether it be in fusion or a fission chamber?
Oh, of course. You could use something like this as a coating. I had never thought of that. And you would apply it in a fabrication environment, so that you would make a nice smooth coating layer on something. Yeah, of course you could do that.
What advantage would that have if you were to use it?
Well, I'm trying to think the advantage of this over other kinds of coatings would probably just be in its composition, and in terms of you could put material in there. Maybe you wouldn't want to use silicon carbide, but maybe you'd want to use something maybe that had more boron in it, which has a high absorption cross section for nuclear processes, like in this particular example. But it'd basically be a glassy spackle compound that you could put a glaze type coating on material that you would be using in a reactor. So sure, you could use it for that, and you change the composition so that it would be useful in the environment that you wanted.
And kind of continuing along a similar train of thought, could this be used as a dense medium for radiation?
Yeah, well, yeah, possibly, but you have to remember this stuff ends up making a fairly thin coating, and so thin coatings don't typically block a lot of radiation unless they're specifically tuned to absorb the radiation in question. So maybe you could think about what kind of radiation you wanted to absorb, and then use the vehicle technology, which is a silicon oil, coupled with the frit material, and maybe some other powdered material that you put in there that works well to absorb the radiation that you're interested in. But you're probably not going to have a layer too much thicker than a millimeter, and so you'd have to make sure that the absorption properties of this over the path length of a millimeter would do what you want.
Well, it's back to me, and along those lines, it seems that it could be used as a coating or maybe as a filler or a frit material, and then also as an etching agent. In your mind, is there an immediate avenue that you've thought of this could be used here in one of these type of applications, or one that we didn't mention here?
There's an application. Sometimes you have ceramic materials that you want to bond together, and so one way is you just glue them together, but most glues break down and come apart at high temperatures. So say you had two different kinds of ceramics discs that you wanted to bond together that were subsequently going to be used in a high temperature environment. You could use this kind of a compound as a means of bonding the two pieces of ceramic together, that once you did the initial heating and bonded them together, then you would have a permanent joint that could withstand subsequent heating and cooling events. So you might be able to use it when you're bonding ceramics together.
All right. Well, on top of that, we were doing just a market search on glue, and what does the industry for producing glue look like? And we saw several different uses for them, specifically in a vacuum, but then also out of vacuum. Things like the medical industry, construction industry, high technology industry. Is there one of those industries, just in a broad sense, that you thought, hey, this also could be used there?
Well, the real uniqueness of this stuff is that it works in a vacuum, and I think if you look at bonding agents, frits for bonding ceramic together, where you are in a normal atmospheric environment, you can put it in a standard furnace or kiln and you can bond ceramic together. I think you'll find that there's all kinds of pre-existing concoctions that work well. But what there isn't are these bonding concoctions that will work in a high vacuum. And that's what this material was, that's why this material came about, was we needed something that would work in a high vacuum, and it couldn't just be a powder, because you can imagine what a powder would be like in a weightless environment. It'd just form a big cloud around you. So it needed to be kind of a putty liquid material that would behave well in a vacuum at a swing of different temperatures, from maybe minus 50 centigrade to temperatures plus 50 to maybe 100 centigrade, because those are the kind of temperatures that you could have when you're working in a space environment. So that's where this stuff really shines. And it may not compete well with pre-existing bonding agents for ceramics and metal to ceramics, where you can have the pleasure of working on them surrounded by a normal atmosphere, and you cook them up in a normal furnace. So I would really look at vacuum kind of operations.
Well, Mr. Pettit, or Dr. Pettit, we appreciate very much. There's one last question. As we were researching your, unless you guys have another one, but I'll ask this one, and then if you have another one. We looked at 4 different inventions of yours, and which, personally, I thought the cup was fascinating. The glue and the cup were both fascinating for us. All of them were, but that cup, how the liquid would just self-propel itself up to the cup, and you just pull it off the rim. Am I describing that correctly? Is
Yeah.
the way that works? Well, all those other 3 went to a patent stage, and so the question we wanted to know an answer to was, why did this one not go to a patent stage?
Oh, the glue, it depends. When you work for an institute or a big company doing technical stuff, anything that you invent while you're being paid to invent it basically belongs to that company or the institute. And it's that way at a university. It's that way if you're in industry. It's that way if you work for the government. Whoever is paying your salary owns the intellectual property of everything that you invent. And that's only fair because they're paying your salary, providing you a laboratory and all this other stuff. And so when you invent something, you can write up an invention disclosure, which is a sort of a poor man's patent, in that it describes the invention and all of that, but it doesn't have all the legalese format to it. And then you turn it over to the legal department of your institution, and then they make the value judgment as to whether there's enough economic return to warrant the patent process, because doing patents can be expensive. You can spend tens of thousands of dollars to go through all the process of getting a patent issued. And so you have to have an invention that has some promise of economic return in order to go through that. And so whenever I come up with something that I think is noteworthy, I'll write up one of these invention disclosures and then turn it over to the NASA legal intellectual property people, and then they make the decision as to whether to pursue the patent. And with this DPG, with this glue, I think they decided that there wasn't enough Earth-based applications to warrant pursuing a patent on it. And if you look at where this stuff really shines, it's meant to be used in space for repairing your spaceship if it's been whacked by space debris. And there's not a whole lot of commercial need for that right now. Maybe in 50 years there will be, but right now there's not a lot of need for this stuff.
Well, just one follow-up to that. You invented this in response to the catastrophe and the tragedy with Columbia. Has it been used? Have you been able to use it in space for return?
No, fortunately not, because if you needed to use this stuff, that meant that you got whacked by some space debris and you were in a world of hurt, so to speak. And fortunately, we were able to avoid any of those occurrences during the remaining period for the space shuttle. But we're NASA, which means we wear both belts and suspenders, because, if your suspenders fail, you got the belt. And if your belt fails, you got the suspenders. and it keeps your pants from falling down. And we're NASA in that we always have a contingency in our hip pocket, a plan for a contingency. And so we had a number of different repair techniques for a shuttle leading edge and shuttle tile, just in case we needed that for the remainder of the shuttle program. And as it turned out, we didn't need any of these repair capabilities, but we had them available.
Very good. Well, thank you for your time, and I look forward to hearing questions posed to you by faculty and students and listening to those answers also. Dr. Z?
Okay, so once again, if you have a question, I'd like you to come up to the mic so that we can get it recorded. I don't know, does anybody have a question that they'd like to follow up with, please? Okay.
Sir, I'm Robert Matthews, and I teach in the entrepreneurship program here. And we're going to be taking a look at some of these ideas as well. A couple questions. This is basically a short-term application as you've described it. Do you see it as having potential for long-term, for something that would be more permanent as well?
You mean in terms of this glue material for patches?
Right.
Not really, because if you look at the original application, it was for fixing leading edge on the space shuttle. If you've got a big hole in the leading edge of the space shuttle and you've managed to patch it and limp on home and you're still in one piece, you're going to want to take that chunk of leading edge off and put on a new one. And then you could take the piece that you repaired and you could put it on display at a museum and talk about how the repair technology worked. But I don't think you'd want to keep flying with a patch on your leading edge. So the whole point of this was just something that was going to be temporary, that would allow you to get yourself back home and still be able to talk about it.
Understand that, and that was kind of the basis of my question then. In other applications, not involving that, is it something that might work long-term somewhere?
Yeah, well, it could, because it makes a permanent bond, and I'll just invent something here just because we're in the process of talking about things, hypothetical things. Say you had a couple pieces of ceramic material that needed to be bonded, but they needed to be bonded while they were in a high vacuum. Maybe it's just because they had some kind of special coating on it or something, and if they were subjected to Earth atmosphere and heating, they would get oxidized or whatever. So you're in a ultra high vacuum chamber with these two pieces of ceramic, and you could put this material between the two pieces of ceramic, set it up in your vacuum chamber, pump down remove all the gases, and then heat this stuff up, and then you could bond it, and then after the bonding process, you could cool it down and remove it from the chamber, and then use this material for whatever it was designed for. In that application, it would make a permanent bond that would be more than just a temporary patch.
Thanks. And a couple other things. What about, how would it work if, would there be any problems with it in an environment where either hydrocarbons or water were present that you see?
Probably not. You'd have to look at the borate glass compounds, and again, you can formulate this to the idea is that you have a silicon-based oil with a number of other compounds that you add to it, and you can add borate glasses. And I added the borate glass specifically to make a lower melting point material that would wet the leading edge of the space shuttle. But you could add other different kinds of glasses to the silicon-based oil that weren't boron or borate based. So you could add calcium oxide based glasses. You could, flint glass is an example where you have sodium and calcium based glass. Again, these things are a lower melting point, but they're not based on on the borate chemistry. And because borate glasses can be attacked by the environment. They can be attacked by water to a higher degree than glasses that don't have borate in them. And you can even use other oxide materials like lead glass. It has lead oxide in it, and of course you don't want to use that for dishes and things that you'd serve food on. But lead-based glasses have certain properties that may be desirable, and you could add lead oxide to this material and basically make a lead-based glass compound. So it doesn't have to be borate-based compounds. The borate was just based off of what I needed for the leading edge. And from an environmental point of view, the borate-based glasses would be attacked more by water or acid rain and other kinds of fades that normally would be presented in just a weathering environment. But by changing the composition, you could make this materials into something that would be resistive to the environment that you might be in.
Well, thank you again. Let me echo the thanks of others for spending time with us this morning.
Oh, this is fun stuff. A lot of times in your daily grind here, even as an astronaut, you don't get a chance to talk about all these fun ideas. You got to talk about flipping switches in a spacecraft to keep its control the way you want it. And being able to talk about ideas like this is really fun.
Hi, Dr. Pettit. My name is Nathan. I'm a chemistry major here at Sam Houston. I had a couple of quick questions. You keep saying this compound sets on the leading edge of the space shuttle during re-entry into the atmosphere. What is the minimum temperature that this compound decomposes into glass at?
Probably around 1,200 degrees centigrade, something like that. And it starts to flow around 1,200 centigrade, and then it's stable up past 2,000 degrees centigrade. So at least that's what it showed during the testing that we had in the vacuum chambers. And we did a lot of the testing at NASA Langley in back east, where they have these pretty substantial vacuum chambers that could be heated with an ion stream equivalent to atomic oxygen. And because you're going really fast when you hit the upper atmosphere, and there's a lot of atomic oxygen, which is really corrosive to anything that could be oxidized, which is why carbon-carbon composite just disintegrates unless it's protected with a thin coating of silicon carbide. And we've got these chambers where we can simulate the entry process at temperatures and pressures and compositions of the upper atmosphere.
Okay, thank you. The reason I ask, though, is could this be feasibly set, its compound set with, say, an acetylene torch? Or
Oh, yes. Yeah. In fact, a lot of the studies that we would do, we'd use an acetylene torch to do on test coupons, where we'd maybe have 20 different variants of this, and we'd have little coupons that maybe be 2 inches square, and we could in a short period of time heat 20 of these coupons with an acetylene torch. Of course, this would be at atmospheric conditions, just to look at the melting and the wetting properties. And then from a test like that, we could choose 2 or 3 of the compounds that looked like they had the most promise, and then we could do more extensive testing in a vacuum chamber with those. So you're thinking along the right lines in terms of, is there some way that we could do simple heating to do testing so that we don't have to do the expensive and oftentimes slow process of vacuum heating and under the conditions that we wanted.
Thank you. One other quick question. I don't know how quick the answer would be, though. We keep saying that the bond is permanent. So it would be a glass bond to the surface of the metal or a ceramic, such as the space shuttle. How exactly is it bonding to this surface? Covalent bonds, ionic bonds?
It would be covalently bonded. especially at the kind of temperatures that the glass forms. They're covalent bonds. They're definitely not ionic bonds. And van der Waals forces and things like that are way too weak. This would be peeling off if it was just van der Waals forces. So it forms covalent bonds with the material, the substrate.
Do you have other questions?
How's it going, sir? I was wondering, would your glue, does it hold any insulation properties? Could it be used in any kind of, like AC kind of conditions and hold in any temperatures?
Oh, that's an interesting question. I never thought of that before. Probably not, because, well, it's got properties. Think of it as a glassy. After it's heated and formed this bonding layer, it's like a glassy material. So its thermal coefficients are going to be close to that of regular glass. So you typically don't think of glass as being a really good insulator, which is why we have thermal pane glass, because the dead air space between the glass panes actually acts as the insulating material, not the glass itself. So I would think that this would be considered more of a conductor and with the same kind of properties that glass would have. Definitely not a conductor of heat like metals, but a conductor more in the same realm as what you would have with just regular glass.
Okay, and then my second question is, could it be used to fill holes in maybe glass windshields? Would there be a way to change the visual properties of it away from that dark green to a see-through substance and use to fill like maybe rocks that have come up and put a hole in a windshield or cracked a windshield to seal that?
Oh, yeah, this is why it's great to work with students, because see, I'm so bent on trying to solve specific problems dealing with space flight that my mind isn't wandering outside the box and working with a whole classroom full of bright-eyed students. You guys come up with all these really clever ideas. I would have never thought about trying to use this to fix a windshield on a car. That's an interesting thought. I need to think about that a little bit. Generally, if you've got a cracked windshield on a car, any kind of extra stress you add to it makes the crack creep. And if you have a little crack on the windshield of a car, if you push on it a little bit, you can see the crack go zing and grow across the windshield. And local heating on a windshield would probably make the cracks grow. And so you could have this material, you could wick it into the cracks, surface tension might wick it into the cracks as a liquid, and then applying the heat, maybe you would need to have a material that would glassify at a much lower temperature. And what I'm thinking is you might just want to use some concoction of the silicon-based oil without any added frit, because if you've got a little narrow crack, the oil could creep into the crack, and then you could decompose the oil and make a glass bond, and so that would be the crack phase, where you might have a big chip or a divot in a windshield. I'm trying to think what would be good to fill that up. Anyway, interesting idea. I hadn't thought about that. You need to run with that, and maybe you could make a different formulation of this that could be used as a windshield repair. Then you could stand at the street corners and put a sign up where it says free windshield repair.
And then my last question is, do you have any worries, or are there any situations where moisture may be able to get under the glue and affect it in any negative circumstances?
Well, for my application, no, because you're exoatmospheric and you're in this ultra high vacuum of space, and there's no moisture around. So for my application, no. If you look at using this on Earth, if you're doing it in a vacuum furnace, by virtue of pumping the furnace down into a vacuum, you're going to drive most of the moisture off. And then after you start heating it, you're going to drive even more of the moisture off. So if this is a high temperature operation, I don't think there's going to be much moisture around. If you figure out a way to cure this at a much lower temperature that maybe you could use for windshield repair, then you might have to worry about moisture being there.
Thank you, sir. And thank you for meeting with us.
Oh, hey, this is fun. I'll tell you, I wouldn't miss this. Actually, if I wasn't stuck here doing my day job, I could go to school and be a student again. I'll tell you, it's really fun to sit there and learn all this neat stuff.
Other questions?
Hello, sir. My name is Eric Watts, and I'm a student in the entrepreneurship program. I've got a couple questions. As far as the time it takes to apply and then for it to sit and be ready for use, about how long does that take?
Well, applying it could go real quickly because you have something that looks like a caulk gun with this glue in it, and you just squirt a little bit of that stuff out, and then you just smear it around where you want, and put your patch over the top of it, and there you go. So it's just how long does it take to take a dollop of this stuff and smear it around. The curing process occurs over about 6 to 10 minutes, which is the entry process with the heating. So you do your deorbit burn and you lower your altitude, and you're actually going faster because you've converted your potential energy into kinetic energy. So when you hit the atmosphere, you're actually going the fastest. And then the atmospheric drag starts to slow you down, which is exactly what you want. But the drag generates the heat. And that's what makes your spacecraft burn up unless you got the heat shield there. And so it's the heating process in atmospheric entry that cures this material, and that occurs over, say, a 5 to 10 minute period. Now, if you wanted to do this for earthly terrestrial applications, you'd put it in a furnace, and just because of heating rates and things like that with expansion and contraction of other materials that you might want to bond, you might need to do the heating slowly. So it might take a couple of hours to come up to temperature, and then a couple of hours to lower the temperature, and which is commensurate with any kind of ceramics. If you want to make a ceramic bowl or a ceramic pot, it takes about 6 hours to fire these things in a kiln, just because of the expansion and contraction forces will crack it if you do it quickly. So I imagine the same kind of thing. You'd want to heat it slow enough so that the expansion and contraction forces in whatever the substrates were would not make everything warp and crack.
Okay. And you said it could be applied to metals, say cast iron, possibly?
Yeah. Particularly with the borate materials, the borate glasses will wet metal, and it actually keeps the metal from oxidizing once it gets wet. So as, say, you have, and what we had were some of the screws that we were fastening the patches on the leading edge were made out of a molybdenum-based compound. And the molybdenum-based compound, a steel compound, would oxidize and burn through real quickly in the atomic oxygen during the heating process of entry, and then the bolt would fall apart, and then your patch would fall off. And what we found was this material would melt and coat the molybdenum steel-based fastener and keep it from oxidizing, and so it would actually protect the metal parts. And so these metal parts get a thin layer of this glassy material over them, and in the heating process, it would actually bond to the metal. So cast iron, stainless steels, molybdenum-based steels, if you have the right formulation, this material, when it's hot, will wet those metals.
And again, with, I guess, application, is there a minimal or a maximum temperature to which you can apply this?
Yeah, well, again, it depends on your formulation. And my formulations were all done so that you had to be over 1,000 centigrade before this stuff started to melt in free flow. And then it could withstand upwards of 2,000 centigrade for the heating process going through atmospheric entry. If you chose the right kind of materials, you could choose lower melting point glasses and maybe apply this at lower temperatures. And if you were really clever, you might be able to figure out some way to fix this so that you could do real low curing, temperature curing, and fix windshields on cars. I really like that.
All right, thank you, sir.
Dr. Pettit, my name is Joe Kavanaugh. I teach in our management faculty here. I'd like to change the conversation in the last few minutes. We have a lot of entrepreneurship students and students in innovation. I'd like for you to talk about the innovation process, where ideas come from, and what it takes to be an entrepreneur and innovator.
Okay. I can talk about this stuff for hours. Yeah, I think everybody can be an entrepreneur. Everybody can create new things. Some people are better at it than others. It's just like not everybody can be an NBA basketball player, but everybody can learn to play basketball to some degree. And so one of the goals in terms of either industry or teaching at university is to try to make people blossom and expand their abilities to the best that they are able to do. And one way of doing that is to work in groups and to not have a lot of rules in terms of what you can and can't do. You basically have to be able to think out of the box, which is a cliche. And one of my colleagues, I kept saying, you got to think out of the basket. And by virtue of saying that, shows that he was thinking outside of the box. And so where do the new ideas come from? I really don't know. They just seem to happen. But you got to be in the environment where you can't be afraid of coming up with something that sounds crazy. Because if you come up with something that sounds crazy and everybody castigates you, then you're going to eventually keep your mouth shut. And so you got to be in an environment that allows innovation to take place. And I don't think you need to have an innovation center. I know in business now, they're starting to build these innovation centers, which you'll have a room that has all kinds of brightly colored furniture, and maybe you'll provide a coffee machine and that kind of thing. And then they want people to sit around and innovate. And that may very well provide an environment that helps. But I think you can have a dingy place in the basement of a building that will also allow people to escape and innovate.
What are the conditions at NASA that allow and foster innovation?
Having a really motivating mission helps. And when you have human beings flying in space and going off into this harsh frontier, that really motivates people to innovate. And let me use an example that I'm really proud of. There's a snicker factor, but it shows the innovative nature of NASA engineers here. The last spacewalk we did, we had a malfunction in the spacesuit, a rather serious malfunction where it started to fill full of water. And we use water in the spacesuit for cooling, and then it actually freezes in an ice pack on the back of the spacesuit and sublimates away. And that's how you get rid of the heat generated within the spacesuit, because you're surrounded by a vacuum of space and you can't use conduction. You can't use convection to get rid of your heat. You can only do radiation, or in this case, sublimation. And so we've got a couple gallons of water built into the spacesuit. Well, there was a malfunction in the spacesuit where the water started to leak out inside, and it leaked out in the helmet. And nobody had thought about this implication before, because when you get water on human skin, it sticks to human skin and just creeps around. And it started to leak out and cover the astronaut's face. And it's kind of creepy when you get this water crawling all around your face and covering your nose and enough of it probably possibly could have creeped out to make it so you couldn't breathe. So here you are surrounded in a vacuum. You're inside of your little bubble and it's filling full of water and you could drown. And so they terminated the EVA and everything was okay. But it brought up forth the question of how can we keep this from happening again? And one is you got to make sure, you got to figure out why you got this water leak in the first place. You got to fix that. But then what happens if you get a water leak in the future? What could you do? And so the NASA engineers were thinking about this. How could we keep the water from wicking around the person's face if you did happen to have a leak and possibly suffocate you? And someone thought about, well, gosh, we wear diapers. And in the suit, you wear the diapers so that, you're in the suit for up to 12 hours, maybe 6 or 7 hours during the EVA and sometimes up to 4 hours more inside the airlock getting ready to do the EVA. So you're in the spacesuit sometimes for up to 12 hours. And, you got to provide for human beings needing to go to the bathroom. And so you wear a diaper and it works really well. And it controls a fair amount of water that's being released in the suit, but it's just being released around your waist, right? Well, someone thought, well, hey, we could wear a diaper on our head. And there's a big snicker factor about that. You're going to wear a diaper on your head. But the basic premise behind that is really, really sound. And so initially, they took the diapers, which were meant to go, where diapers normally go, and you could kind of tape it around a little bit. You could stick it on your head, and it would work. And so now NASA being what NASA is, we formulated a special diaper. We don't call it a head diaper. I forget, we come up with some other fancy name, but it's basically a custom fit diaper that fits on the back of your head so that if you had this malady again, it would absorb the water and keep it from moving around in front of your face and possibly suffocating you. So there's an example of innovation that one is kind of funny. It's fun. I mean, it's like, wow, we put a diaper on our head. There's a snicker factor about it, which could create some inhibition to even thinking about this as a solution in the first place. But it's a real elegant solution. Solutions don't necessarily have to be sophisticated. You don't need to have a computer chip with process control and valves and pumps and all this stuff to suck the water off of your head. You might be able to do something just really simple and elegant with an absorbent that sounds a lot like a diaper on your head, but of course we're going to call it something else.
Well, Dr. Pettit, thank you. That took us someplace I never expected to go.
But it just shows that there are real solutions, and at NASA, when you have a person out on a spacewalk and they have a problem, it's no longer minus 10 points on a homework set anymore. You can pay for some of your maladies with a pound of flesh in the Shakespearean sense of the word, and this leads to people really thinking and really innovating on how can we resurrect a bad day, and that kind of environment with a overpowering mission, I find leads to a lot of really neat innovation. And here at NASA, there's no shortage of needs for innovation just because of what we do for a living here.
Dr. Pettit, I want to thank you for spending time with our students. We truly do appreciate that. And I'd like to give you a nice round of applause.
And so just keep in mind, everybody here, all the students that's listened to this, you can go out now and put a diaper on your head and walk around campus, and you can legitimately say that you are a true innovator.